quantum mechanics and thermodynamics are separated by decades of experience and knowledge about our universe, and yet they are intimately related. In this fascinating new book called Quantum Steampunk by Dr. Nicole Yunger Halpern, we go on a journey through the deepest annals of thermodynamics to the most cutting-edge knowledge that we have about quantum mechanics. She's a delight to talk to. We talked about Maxwell's demon. Ooh, so scary. We talked about the irreducible quantities and qualities of quantum mechanics and thermodynamics and how they can be melded together. Of course, I ask her my thrilling 3 patented questions at the very end. You'll want to stay tuned for that. And if you take nothing else away from this, you will get a delightful journey to the Victorian age, sort of a throwback to Burning Man, in a thermodynamic sense, of course. So come along on this journey into the impossible with Dr. Nicole Yunger Halpern. Let's go.
Any sufficiently advanced technology is indistinguishable from magic.
And ladies and gentlemen, children of all ages, step right up for a steampunk adventure. Today's episode is with the incomparable Nicole Yunger Halpern, who was referred to me by a mutual friend, Professor Stefan Alexander, my oldest best friend from Brown University. And he just sent me a cryptic email intro to today's guest. And he said, you have to meet her and you have to have her on your show. And whatever he says, I do, except for try some Jamaican jerk chicken recipe or Trinidadian tri-tip that once caught my mouth on fire at a Trinidadian restaurant in Boston. We're not going to talk about that. We're going to talk about even farther back in the past to the Victorian steampunk era with today's wonderful guest, Dr. Nicole Yunger Halpern, who is a joint fellow of the QICS, the Joint Center for Quantum Information and Computer Science at the University of Maryland. And that is where I believe you're joining us from, right, Nicole?
Yep, I'm in Maryland.
How are you?
Doing well. It's great to be here.
It's good to have you here. I love this book. It's published by Johns Hopkins. I always forget. Is it Johns Hopkins? It's Johns Hopkins, but it's Johns Hopkins University Press, a lovely imprint. We've had on several guest authors from there. And so, Nicole, I always love to start off by asking my authors who grace me with their presence the question you're never, ever supposed to do and ask, and that is to judge a book by its cover. But in this case, this is your first book, if I am not mistaken, and it's an unusual book in a delightful way. But what other piece of quantum information or classical information do we have to go on besides the title and the cover? So I want to ask you, how did you come up with the title and the cover in what we call judging books by their covers?
So I work as a researcher at the intersection of 3 fields: quantum physics, information science, and thermodynamics. And I see this intersection of fields as sharing the spirit of steampunk. Steampunk is sometimes seen as a genre of science fiction. It's a genre of literature, art, and film. It features Victorian settings, so some of the earliest factories that are belching smoke into the smoggy London air, and Sherlock Holmes, and men in top hats, and women in petticoats. There are these settings together with futuristic technologies like time machines, dirigibles, and automata. So steampunk has this wonderful sense of adventure and nostalgia that comes from reaching back into the past and reaching into the future. My work involves, as I mentioned, thermodynamics, which is the science of energy, so the different forms that energy can have and the way that energy can transform amongst those forms. Thermodynamics was developed during the Industrial Revolution, which was being powered by some of the first steam engines, and people wanted to understand how efficiently engines could pump water out of mines and power factories. So thermodynamics developed during the Victorian era to describe big classical systems like steam engines. But today we have great control over technologies that are much, much different, that are small scale and quantum, that could consist of just a few atoms or molecules or even photons, particles of light. In the context of quantum information science, we can use strange quantum phenomena like superpositions and entanglement and quantum uncertainty to process information in ways impossible for just classical systems. For instance, quantum computers will be able to solve certain problems much, much more quickly than any computer that we have today. So quantum computers and other quantum technologies are partially futuristic because we don't have a large-scale quantum computer yet, but they're also cutting-edge science. So we need to adapt the thermodynamics of the 1800s to be able to describe these new small and quantum settings. And so this intersection of thermodynamics and quantum information science I see as sharing the character of steampunk because it reaches back to the 1800s and also ahead to the future. So that's where the term quantum...
And the subtitle is The Physics of Yesterday's Tomorrow, which kind of sounds like a Janis Joplin song, but and walk us through the cover. The cover has this unusual, goggles that maybe I've seen in my Burning Man days, which are far behind me. But nevertheless, what is that? These optics on the front. What does this represent?
Yes, I wish I could take credit for the cover because I love it, but unfortunately, I can't take any credit. My acquisitions editor at Johns Hopkins University Press, Tiffany, was working with an artistic team to create the cover. And so those goggles come from how quantum steampunk costumes tend to feature goggles. Fans of steampunk dress up in costumes with top hats and corsets and goggles and all sorts of other Victorian/futuristic looking paraphernalia. So that's where the goggles come from. And one of the goggles has a cartoon of an atom on it to invoke the quantum nature of this combination.
Yeah, it does kind of have this beautiful whimsical approach to it, which I found really delightful. And it was evocative to me, in my humble opinion, of a book by a past guest. You may have heard of him. His name is Sir Roger Penrose, and he wrote a wonderful book that actually was the first popular science book I ever read. Not that I understood it when I was about 16 years old in high school, and he inspired me, and it was called The Emperor's New Mind, and it's about minds and machines and artificial intelligence, but it's also this whimsically, illustrated work, and it has connections to some of the topics you talk about. And I want to start with something I find, delightful. And I actually used it in my conversation, which aired with Professor Sarah Walker yesterday. We're recording today is St. Patrick's Day, March 17th, 2022. But I aired an episode with Sarah Walker yesterday on the 16th. And in it, I quoted you. So you'll have to watch that episode for a shout out. But I talk about how in your book, you talk about entropy. And entropy is this magical, mysterious thing. And you quote, maybe it's von Neumann or some other, Hungarian or so forth that makes a lot of appearances in this book. But you quote, like, when you don't know what to call something, call it entropy. And I wonder, what is entropy? If I wake you up, an intelligent alien or me wakes you up and, gives you the 3 a.m. phone call that people in Washington talk about all the time. How do you answer that? What the heck is entropy? What does it mean to you at a core visceral level?
Yes, that's a great quote. So entropy comes to us in one sense from basically thermodynamics or statistical mechanics, which is very closely related to thermodynamics. So it showed up there during the development of thermodynamics. And then it showed up in information theory, which was developed by Claude Shannon in the 20th century. And Claude Shannon explains why he used the phrase or the name entropy for this quantity that he had put together for some mathematical reasons to explain or to quantify the efficiencies of some information processing tasks. He says that he did talk to John von Neumann, this amazing Hungarian-American mathematical physicist, And von Neumann told him, you should call it entropy for two reasons. In the first place, this function that you've come up with in information theory, it's already been used in statistical mechanics under that name. And in the second place, nobody really knows what entropy is. So in a debate, you will always have the advantage. And so that's why I do information theory.
So I have a question that's always kind of plagued me, which is the notion of whether or not we really have a good understanding of what constitutes, say, physics or thermodynamics. And in essence, my question is, where does physics end and where does chemistry begin? I mean, I think of thermodynamics outside of the quantum thermodynamics you describe here. It's almost like chemicals and molecules and not necessarily divorced from chemistry. But I guess my crisp question, where is there a hard dividing line, a bright line between chemistry and physics in terms of micro and macroscopic perspectives?
One thing that really appeals to me about thermodynamics is that it is so general, and it's a theory that applies to and governs many other theories. So cosmology, as you're aware, obeys thermodynamics, and biophysics and condensed matter and atomic, molecular, and optical physics. So all different scales across the universe obey this sort of overarching theory. So thermodynamics does show up in physics and in chemistry and in engineering. When I was in biology class in 9th grade and learning about the phylums and genuses and species and so on, my teacher said, there are some people who are lumpers and some people who are splitters. Which one you are determines to what extent you think that different organisms should go into the same category or into different categories. Although I'm very fond of organizing things, so there's part of me that's naturally a splitter, I'm very much a lumper in that I love interdisciplinary studies. And I think that what I'm doing is just theoretical physics. And I can do theoretical physics while collaborating with a chemist who thinks of himself actually as a physical chemist in some cases. I think that maybe it's not so important, at least to me personally, and in my work, it's not necessary to draw these dividing lines, because I think it can be so valuable to reach across disciplinary boundaries and instead.
One of the most fascinating aspects of both this book and thermodynamics in general is the concept of these demons. And there's a few different demons who make their appearances here, and they're not malevolent demons, don't worry. But talk about this concept of Maxwell's demon. And I've heard claims, and it seems like there are oftentimes, Sabina Hassenfelder, past guest on the show, jokes that, every time the black hole information loss problem is solved, she tweets out, black hole information loss solved again. And she's been doing this for like 10 years now. But I often hear this about, things like Maxwell's demons and the second law of thermodynamics. Can you explain what is Maxwell's demon? And then recent claims, that have been postulated that you could actually evade the second law of thermodynamics in a sense. So that'll require you to define the second law of thermodynamics. So first, what is Maxwell's demon? Why does it feature so heavily as not a villain in this book, but sort of a thematic, the resonance in this book?
The second law of thermodynamics has many different faces. There are many different ways that you can state it. One way to state it is if you have any closed, isolated system, like gas in a box, then its entropy, which is some, I guess I can get to in a moment what I think of entropy as. Its entropy either grows or stays constant, but does not decrease. And this growing of entropy is how we might think of the arrow of time. Now, I think of entropy as a measure of how many different configurations a system can be in. So if you have a gas in a box, then this molecule can be over here, or over here, over here, or over here, and it can have many different momenta. And the more ways you can arrange the particles in the box, and the more different momenta you can give the particles, the larger the entropy the system has. So if the particles are all clumped together in one corner of the box to begin with, then if they're just limited to that one corner, then there aren't so very many ways you can rearrange them. But if you start with them all clumped together in a corner and then you wait, they will spread out all across the box, and there will be many, many, many more configurations available to them. So the entropy of this gas in a box increases as time goes on. So this rule was developed a long time ago, and some people thought that they could get around it. And even today, I think it's fun to come up with thought experiments to see to what extent we might try to break the second law of thermodynamics. To my knowledge, there is no breaking of the second law of thermodynamics. One could bend around the second law of thermodynamics, maybe by setting up a scenario that doesn't quite obey the assumptions behind the second law of thermodynamics. But as far as I know, it's still going strong. And one of the tests that a number of us think it has stood up to is the Maxwell-Demon paradox. So James Clerk Maxwell was a British scientist who was also famous for coming up with a unified theory of electricity and magnetism. He said, okay, suppose that we have this gas in a box whose entropy properties are supposedly so simple to understand. And suppose that there's a partition in the middle of the box, and there's a little doorway in the middle of the partition. Furthermore, there's a finite being, as he called it, later colleagues of his called it a demon, who can open the door and let particles through, or close the door and prevent particles from going through. Suppose that this demon watches the particles and finds that some of the particles move toward the door with a high speed. Anytime that particle moves with high speed from the right of the box, then the demon lets it through. And anytime a particle approaches the door with a low speed, then the demon lets it through into the right-hand side. Particles, if you have a gas, then its particles are moving at certain speeds, and the higher the speeds of the gas particles, the hotter the gas is. So eventually, all of the slow-moving particles are going to be in the right-hand side of the box. So the right-hand side of the box is going to have a cold gas, and the left-hand side of the box is going to have a hot gas. So the demon will just use his measurements and his control over the door in order to create a temperature difference. Now, if you have two different gases at two different temperatures and you have an engine, then you can let heat flow from hot to cold through the engine, and you can use the temperature difference to perform work, like powering a car or a factory or pushing a rock up a hill or charging a battery. And after you have performed this process with the engine, then the gases will have mixed again, and you'll have just one fairly uniform gas spread out across the box. So, and the demon could do this many, many, many times. And one can argue that the demon does not himself increase or experience an increase in entropy, and also ideally, in at least theoretical physics, in principle, as we say, the engine does not need to experience an increase in entropy. So you could power as many cars as you like, while again and again just returning the gas to the same initial state. So it seems like you can accomplish a whole lot, get a whole lot of work out of this gas without really changing its state. And that just seems wrong. And in fact, it violates the second law of thermodynamics. So Maxwell said, ha, what do you make of that? And there has been a lot of debate about Maxwell's demon. There is not complete agreement throughout the physics world, but quite a lot of agreement in the physics world that Maxwell's demon paradox has been resolved by a few steps. There was another great Hungarian-American physicist called Szilard who made the first step, or one of the first steps, and then Rolf Landauer, who was an information scientist at IBM. And these steps were put together with a bit more by Charlie Bennett, who is an information scientist at IBM. And he says, we're actually missing something important about the demon. So when the demon measures particles, then he records in some memory each particle's speed. And if we really want to argue that the gas ends up in the same state as it was after the engine is used, then really the whole system has to end up in the same state, the daemon as well. And so the daemon has to erase his memory. Now, it had been shown by Landauer that erasing information costs thermodynamic work. So the daemon can extract work from the temperature difference, but he'll have to use that work in order to erase his memory. And so on balance, he'll get no net work out of the gas in a box. And so the second law is a number of...
Yes, and you mentioned Lauder, and we'll get to that. There's another kind of a topic that your response kind of elicited in me, and that had to do with these quantum, teapots that you talk about quite frequently in the book. And this is not unrelated, I think, to the same sorts of issues of Maxwell's daemons, in that you have this incredible, kind of minimalistic, in a good sense, way of distilling down these very complicated topics in a way that non-experts, and I'm a non-expert when it comes to quantum thermodynamics. I don't know how many experts there are. It's only been around for a few years, but in its current form. But can you talk about these Szilard, engines and things like that? How do they relate to Maxwell's daemons? Are they just, basically another way of restating this age-old problem, or do they fundamentally revolutionize our understanding of these thermodynamic connections to information? Because as I recall from your wonderful description, it's tangentially related, but it's really about information, these types of engines. So can you explain what those are?
Sure. So Maxwell's daemon paradox involves this simple model of gas in a box. And what Charlie Bennett pointed out was the close connection between the thermodynamic manipulation of the gas to get work and information processing, namely erasure of the daemon's memory. And an important couple of steps on the way to Bennett's resolution of the paradox came from Szilard and Landauer, and they showed through some similar but slightly different, very simple thought experiments how thermodynamic energy and information are very closely bound up. So there are two types of energy that can be transferred in between objects: heat and work. Heat is the energy of random motion of particles jiggling around. It's random, it's uncoordinated, it's not being directly harnessed to do something useful. Work is useful energy, it is organized in a sense, so you can directly use it to, again, push a rock up a hill or power a factory. Szilard showed that if you have information and this useless heat, you can use the information to turn the useless heat into useful work. So he imagined also a gas in a box, because that is one of the favorite settings for thought experiments of physicists. But imagine that the gas in the box is so very simple that it just consists of one particle. And suppose that you have one bit of information about the particle. So the bit is the basic unit of information. It's the information that you have that you learn if you learn the answer to a yes or no question. So suppose that you know that the particle is in the left-hand side of the box rather than the right-hand side of the box. So you know left rather than right, so you know one of two possible options, that's why you have a bit. Then you can slide a partition into the middle of the box and hook up a weight that you would like to lift. Suppose that this is the work you want to do. You want to lift a weight, and in the book, since the book involves Victorian settings, the weight to be lifted in the book is a little teapot, as you mentioned. You can hook up the weight, and suppose that this particle can exchange heat through the walls of the box with an environment that's at a fixed temperature. Then you can unfix the partition so that it can slide across the box, and the particle, which is a gas, will expand against the partition and push the partition to the opposite side of the box. And if the teapot is tied to the partition in the right way, then the teapot will be lifted as the gas is expanding. So the gas expanding performs useful work in lifting the teapot. by the end of the process, we've lifted the teapot, we've done good work, but now we have no idea where in the box the particle is. So we've lost our bit of information. Or in other words, we have traded information for work. So information can serve as a resource in a thermodynamic task. And Landauer showed that also the opposite is true, that you can invest thermodynamic work in order to...
And when we hear things about, information destroyed, and I was joking about Sabina's, consistent harping on this issue, what does it mean to destroy information? Again, from a simple sense, I would never do this, but, if I take this book, we go to Burning Man, and we throw it into the bonfire when they're burning the man, how it's clearly impossible to reconstruct it. I understand that there'll be heat liberated from the chemical bonds in here, but if you had the exact same book, same number of pages, same number of characters, but they were all the letter A, every letter was just permuted, and so there's zero actual information. It's total gibberish, the same exact letters, so you can't say there's more ink or less ink. How could you possibly say that the information is not destroyed from doing such a thing, even classically?
Yeah, if you or I looked at the smoke that came from one book burning, that was actually my book, and the smoke that came from the book full of gibberish burning, then we couldn't tell the difference. There's still a difference there, and in principle, if you had great enough control over the smoke and the heat and all the air around and the people around who might have heard the effects of the crumbling paper, then with an enormous amount of effort, you could reconstruct the information that was on the pages. But I agree that that is extremely impractical. So to those of us who are very limited in, or practically limited in the way in which we can reconstruct ashes and sound and so on and so forth into what used to be present, for all practical purposes, the information is unrecoverable. But it is still out there in the world, just the information has dispersed into many different degrees of freedom.
And then in quantum information paradox, or at least in the black hole information paradox, can you walk us through why, this is so monumental that it needs to keep being solved? Can you talk about the black hole information loss paradox and how it relates to this, to this problem of information destruction and conservation?
Suppose that we have two characters, often in information theory settings. They're called Alice and Bob, but those names are used so very book.
Let's say Audrey and Baxter, yeah.
Yes, Victorian alternatives. So suppose that Audrey writes down a secret in a diary, and she doesn't want for her obnoxious little brother Baxter to know it. So she throws the diary into a black hole and says, nothing will come out of the black hole, as nothing can escape from a black hole, as we all know. Not even light can escape. That's why black holes are called black holes. And so my secret is safe. But as Hawking told us, black holes radiate. So Baxter can stay outside the black hole and collect the radiation that comes out. The radiation will look to him like it's at thermal equilibrium, like it just has some temperature and no other interesting properties that he can see if he just performs some simple measurements of local observables, the way that we, poor humans who don't have extremely great control of our environments, do. So there's a little bit of debate about what happens when a black hole gets all the way down and shrinks an enormous amount. But one idea is that it might radiate all of its mass away as Hawking radiation. And so Baxter can collect all of the Hawking radiation that has ever formed the black hole. But again, if he performs any measurement that he's practically capable of performing on this Hawking radiation, all he's going to see is some particles at some temperature and that have no other interesting or notable features. The question is, where has Alice's secret gone? Where has that information gone? And so the idea is that the information is still in the Hawking radiation. It's just spread out across the Hawking radiation. Quantum systems can share information in entanglements, which is a very strong relationship that quantum particles can share. So if some information is spread out in entanglement, then it's not just in one particle, it's not just in another particle, and it's not in the sum of different particles probed independently. It's sort of between the particles. And so in principle, we think Baxter can reconstruct Audrey's secret, but in order to do that, he would have to take all these quanta, all these pieces of Hawking radiation, and do some massively complicated operation on the entire thing, which would be very, very, very difficult. So for practical purposes, Audrey's information is lost to him, although it is still present in the correlations amongst the Hawking particles.
Another fascinating thing you mentioned in the book is this concept of a Boltzmann brain. Let's stick into outer space, stay with the outer space theme, and let's examine what is a Boltzmann brain and what is a Boltzmann balance, and how do these concepts relate? Boltzmann obviously looms large over all of our discussions of thermodynamics, and we'll get into the modern incarnations of Boltzmann. But what is a Boltzmann brain, and how does it relate to this concept? You talk about a Boltzmann balance.
So Boltzmann brains are rather more cosmological than I can claim too much expertise about. The idea is that it's pretty improbable that we should exist as this advanced civilization with quite a lot of conscious beings and order, as opposed to the highly entropic systems that we might instead expect to find across the universe. So you can imagine that this entire civilization has just come into being, fluctuated into being for a fraction of a second, and your memories were just created in this fraction of a second. You haven't actually lived your life up until this point. You've just fluctuated into being, and soon you'll fluctuate out of being. And so people have estimated the probability that we are, in fact, a Boltzmann brain, or the experience of a Boltzmann brain, and argued about the relative probabilities of our being Boltzmann brains, or of our existing in this relatively low entropy state, which kind of seems improbable. The book features what I call a Boltzmann balance. I came up with that term because the term that's used among scientists is free energy difference, and I think that has too many syllables, especially for a book. So I just renamed it. So, Boltzmann balance, or free energy difference, shows up in the concept of fluctuation relations. So these are equations that kind of enhance the second law of thermodynamics. So the second law of thermodynamics can be stated as an inequality. As we said before, if you have any closed, isolated system, its entropy will increase or remain constant. And so it obeys an inequality. An equality is stronger. It tells us some exact information, but the inequality doesn't tell us how much the entropy is going to grow. So it'd be nice to replace the second law with an equality. And also, the second law, strictly speaking, only holds for very, 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 very large systems. It would be nice to have extensions that hold for small systems, such as even single molecules. So there's a family of equations that have been derived over the past few decades. So one of my colleagues at the University of Maryland, Chris Jarzynski, has one that's named after him, although he's so humble. Everyone else calls it Jarzynski's equality, but he calls it the non-equilibrium fluctuation relation, which has even more syllables than free energy difference. But these are valuable equations. They've been derived theoretically and also tested experimentally, for instance, with single strands of DNA and strands of RNA and very tiny pendulums. They've started out as equations that govern classical systems. They've also been extended to the quantum regime. And one reason why they're valuable is they relate properties of equilibrium systems to properties of far from equilibrium systems. So a system is at equilibrium if it's kind of in a boring state. Its large-scale properties like its energy and its volume remain constant, and there's no flow of anything such as energy or particles into or out of the system, no net flow of anything. So equilibrium is kind of boring, but it's thought about a lot in thermodynamics. A lot of the conventional theory of thermodynamics from the 1800s deals with equilibrium because since it is boring, it's relatively easy to describe. But so much of our world is out of equilibrium. For instance, you and I are out of equilibrium as living beings. If we were at equilibrium, we would be dead. Yes. But equilibrium properties, well, they're useful to know about for the purposes of chemistry and biochemistry and pharmacology. So people want to understand certain equilibrium properties of systems. And one of these is what I call the Boltzmann balance. But we can't, it's really difficult to measure a Boltzmann balance. And effectively, we can't really measure it directly because no system is really out of equilibrium during any process that we perform on it. For instance, if we have a gas in a box and we perform some process like compressing it, we compress at some finite speed. So we're going to roil up the gas a little bit. So it's going to come out of equilibrium. So how do we measure these equilibrium properties? Well, my colleague Chris and others showed that some of these equalities, fluctuation relations, can interrelate properties of equilibrium systems, which we want to know for chemistry and pharmacology and so on, like the Boltzmann balance. Those properties can be related to properties of out of equilibrium systems, which we can access. So we can run some experiments on out of equilibrium systems, like by compressing a gas at a quick speed. We can perform a whole bunch of trials, plug our data into one of these equations, and infer those equilibrium properties that are so useful.
Thank you. That's really a lovely and thorough description of this very complicated phenomenon. Another phenomenon that I'm, kind of alternately confused as to whether it's hype or our best hope is quantum computing. You talk about these notions in quantum computing. I'll say something that I heard someone say in response to Richard Feynman, once, who said something about quantum computers, as we know, and had a lot to say about them. But really, they said something like to the effect that, well, quantum computers are great for simulating quantum computers and, describing how quantum computers work. But, besides that, and maybe cryptographic, breaking of cryptography, which again, you hear about all the time, quantum computers can break, all sorts of codes, and then encryption. And then you also hear they can't. And so, first of all, what is a quantum computer? What's the simplest kind of explanation for that? And then, are they good for, are we going to have a quantum iPhone anytime soon?
So quantum computers are technologies that exist in relatively primitive forms, and we're building more advanced versions. A quantum computer consists of particles that obey the laws of quantum physics to the exclusion of classical physics. So my laptop, which I am using to connect to record this podcast, is a classical system. So it obeys Newton's equations of motion, and it obeys the physics of our everyday world. Quantum systems, as I mentioned, can share entanglements, which is a very strong relationship or correlation between particles. And very loosely speaking, a sort of cartoon picture of what entanglement can accomplish is if you have two particles that are entangled and you take them far apart, even to opposite sides of the world, you measure one of the particles, then the other particle will change instantaneously. So so entanglement is an unusual feature of quantum physics, and it can be used to process information in ways impossible for just classical computers, even classical supercomputers. So that's what quantum computers are. There are two different classes of quantum computers. One consists of simulators. These are quantum computers that do simulate other quantum systems. And these have existed for a number of years. I've been working with experimentalists to use quantum simulators, and they've been very useful in discovering or observing phase transition between exotic phases of matter, analogous to liquid and solid, but the phases that are observed with these quantum computers are ones that are unavailable in our everyday world. And also observing features of systems that are, let's say, counterintuitive, according to those of us who study thermodynamics. Then there are, in addition to quantum simulators, universal quantum computers. So these are being built. Currently, we have quantum computers that have 50 to 100 qubits, or basic units of quantum information. We're going to need quantum computers with hundreds of thousands of qubits in order to realize algorithms like the breaking of RSA encryption, which you just mentioned. So a lot of work needs to be done to get to that stage, but I think that most of us in the quantum physics community believes that we will realize these quantum computers. What are some applications of quantum computers? You mentioned the possibility of breaking cryptographic schemes. Fortunately, and these cryptographic schemes are common, so we have used them when accessing and using the internet. Fortunately, quantum physics doesn't only break cryptography, it also offers resources for securing information in ways that classical systems can't, because of the quantum uncertainty principle that's often associated with Heisenberg. Also, I agree, it might sound a little bit dull to say, oh, quantum computers will be very useful in chemistry and materials research and development, but the implications have the potential to be very significant. For instance, in some countries in the world, food security is at crisis levels. In some countries in the world, food security is at the highest level ever achieved in human civilization. So fertilizer is extremely important to the world. And about 3% of the total energy output of the globe is invested in creating fertilizer. That's a lot of energy. Why do we invest so much energy in creating fertilizer? Because we use a process that was developed in 1909, long time ago. It turns out that bacteria can perform this process a lot more efficiently. But they use a molecule, nitrogenase, that's so complicated we can't unlock its secrets on classical computers. But nitrogenase is a quantum particle, so it is natural to unlock its secrets with a quantum computer. So folks at Microsoft put out an algorithm for a possible application of quantum computers to fertilizer. And different companies around the world are trying to find optimization problems and other chemistry and materials problems for which quantum computers might be very natural and helpful.
So I think another way people get fertilizer is using compost, which is decaying worm poop and things like that. And so now I want to go from that to Bitcoin because I hear a lot about how energy inefficient blockchain and Bitcoin in particular is, and how it uses up tremendous amount of the world's energy resources. And yet, when we look at information and converting to heat, if you just look at an individual bit erasure or something like that, it seems to me that both quantum computers could alleviate that. Of course, you need a dilution refrigerator, and you need to supply that with power. But my university covers that as long as I keep paying my taxes, and you, my beloved audience, keeps paying your taxes. But could you imagine two things happening? One, that the environment, the energy cost would come down because of quantum, effects and quantum computing, and that the cost to erase a bit and, cause it to be zeroed out, so to speak, would be so minimal that the energy would go down dramatically. In addition to the, breaking of the encryption, kind of algorithms that are used to secure the blockchain, are there kinds of implications for quantum computing that could, radically alter our, investments and things like that are stored as purely mathematical problems. And I'm speaking particularly about blockchain here, but if you have other examples, that would be great to know too. So what are the implications for, lowering the energy cost and erasure cost in the information processing strictly on future financial instruments like Bitcoin?
Classical computers now, since they're more or less the only computers that we have widely available, are being used to solve problems that, for instance, in materials research and development could be quantum and could involve a lot of entanglement. And in order to simulate a quantum system of some size, the size of the classical system that we need to perform that computation is exponentially large in the original system size. And so this exponentially large classical computer is going to consume a lot of energy. Whereas to simulate a quantum system of some size, we need a quantum system, a quantum computer that's of a somewhat comparable size. So that does offer some opportunity for trying to reduce the energy cost. A quantum thermodynamics colleague of mine, Alexeyev, recently wrote a paper that's related. As you pointed out, we need to cool down systems so that they exhibit quantum behaviors. Mm-hmm. So quantum computers do require very intense refrigerators, which themselves require work or an energy investment. And according to Alexeyev's writing, the view that the community has taken is we're just going to achieve quantum computing at any cost. But an energy cost is a considerable cost to the environment and to the economy. So maybe we should change our metrics in order to incorporate into them not only the accuracy of our answers, but also the energy cost of achieving those answers.
Mm. And, if you were to kind of advise a young person, getting interested, typically this is kind of interdisciplinary, as you mentioned before, this new field, quantum thermodynamicist, which I had to work on with a speaking coach for a long time to get that right. But, how would you advise, say, a young person comes to you, wants to research with you? What do you say to her, to him, as where this field is going to go? There's a lot of hype. There's a lot of promise. There's a lot of successes. It's an early day in some sense. But how would you advise a young person in terms of this field? Would you advise it as a career choice? And if so, what are some of the, not the job prospects and, what kind of starting salary you make, but in terms of intellectual capital, what do you see as the, give me your elevator pitch for a young person to go into this field?
Quantum thermodynamics is in an extremely exciting phase now. It had its roots in the 1930s, and there was a little more development over the ensuing decades, but it's really experienced a burst of activity over the past decade. And that burst is mainly outside of the United States. Finally, Americans are getting interested because of experiments that have been happening. Thermodynamics has traditionally been very theoretical, even borderline philosophical, but over the past decade, we've had increasingly amazing control over quantum systems, in part because people have been developing techniques to control quantum systems because they're trying to build quantum technologies like quantum computers. And we can use those control techniques and use them to realize quantum thermodynamics experiments, test the theory, build quantum engines for the first time. So experiments are growing. I think they're going to continue to grow quite a lot over the next few years. I've been working with quite a few labs that are eager to get into quantum thermodynamics. And so we've been collaborating on taking theory that I've worked on and bringing it into reality. That's going to happen a lot more. Also, an opportunity that I think the quantum thermodynamics community is right now just beginning to pivot to really dig into is practicality. Conventional thermodynamics developed hand in hand with the Industrial Revolution, which was eminently practical. And quantum thermodynamics has, again, been theoretical, it's been foundational, it's provided a lot of great insights and helped us understand better even what the difference is between the quantum world and the classical world. we have designed technologies like quantum batteries and engines and refrigerators, and some of these technologies can even excel, do better than their classical counterparts according to certain metrics. And we started realizing these in laboratories, but at the moment, these experiments are very proof of principle. They're not useful in a practical sense. In order to run a quantum engine, to get it to perform work for you, you have to cool it down, and so spend energy on refrigeration, you have to spend a lot of energy on controlling the system, and you get very little energy out. But there are opportunities to make quantum thermodynamics practical. For instance, I'm working with a lab at Chalmers University in Sweden on creating a quantum refrigerator that services quantum computers, and according to numerical predictions, which have yet to be borne out in the lab, since experiments are just starting basically this week, but hopefully they will be realized. According to these predictions, this quantum refrigerator, according to some metrics, can perform as well as, or maybe even a little bit better than, some of its classical counterparts. So I think that a great opportunity right now for quantum thermodynamics is to yield useful quantum thermodynamic technologies.
And it's interesting, as you point out in the book, frequently resonating is kind of this notion of serendipity, and how sometimes we don't really get what we started off looking for, and you end up getting something in cosmology when you're thinking about thermodynamics, or you end up getting something in thermometry when you think about refrigeration. Actually, that literally happened to me long before you and I met. One of my graduate students, Stephanie Moyerman, who now works at eBay and probably makes twice what I make as a public servant. But anyway, she and I were trying to think of a way to cool our volumetric detectors down as much as possible using pure solid state rather than liquid helium, and which is kind of finicky and frustrating to work with. And so we use these superconducting, superconducting normal tunnel junctions called sinus for superconducting, insulating normal, insulating superconducting, that she really invented. And we were going to use those to cool not like this massive block of focal plane. We realized, you only need to cool this tiny little detector, of superconductor down to close to absolute zero. But why cool down this huge cryostat to do that? Just cool the sensor itself. So we went through it and we found, you could do it, but it added a lot of complexity, and we actually got some cooling power. But on the other hand, it turned out that these little refrigerators were actually self-calibrating quantum thermometers, which was kind of unusual. And throughout the book, you talk a lot about thermometry. And I wonder if you could talk just in the last few minutes that we have together, just sing the praises of the humble thermometer and why it figures so prominently in your wonderful book, Quantum Steampunk.
Existence of a thermometer is basically one of the foundational laws of thermodynamics, often called the 0th law of thermodynamics, because people had already developed the first law and the second law and so on by the time that the 0th law was developed. But the developers thought this is such an important law, it should really come first. So it's called the 0th law. And in honor of that, the book has a chapter 0 for the prologue. So the 0th law of thermodynamics says that, suppose that I have some system, again, in the book, we're in a Victorian setting, so suppose that I have a pudding that's at equilibrium, at thermal equilibrium, with a system that you have, that's let's say a trifle. And the trifle is at thermal equilibrium with a cake of some sort. So then my system is also at thermal equilibrium with the cake. And so thermal equilibrium is transitive. So what do we mean by thermal equilibrium? Two systems are at thermal equilibrium if they have the same temperature. And basically as much heat flows into one system as flows out. So there's a balance. So according to the 0th law of thermodynamics, thermal equilibrium and having the same temperature is a transitive property, and that central system, so your trifle, serves as a thermometer that diagnoses the temperature of my system if your thermometer is used and together with knowledge of the system, of the temperature of the third system. So temperature is a very fundamental quantity in thermodynamics. It tells us about the ratio between, or how energy changes if entropy changes, and vice versa. And it can be tricky to figure out how to measure the temperature of a quantum system, because what do we do in order to measure a temperature? Well, we take some probe system, our thermometer, and we put it in contact with the system whose temperature we want to measure. We let the two systems sit there for a while so that the thermometer can come to thermal equilibrium with, to be at the same temperature as the system of interest, and we take away the thermometer and we read the thermometer. But if the system of interest is a quantum system, then it's very delicate. And quantum systems can very easily interact with any stray particles that are around and lose their quantum behaviors. We say that these quantum systems decohere. They lose their quantum natures and they cease to be useful as controlled quantum systems. So if you want to take a thermometer and put it in contact with a quantum system and wait for a while, then by the time you read your thermometer, the quantum system of interest might no longer be of interest. So people have been developing all different techniques to use other quantum phenomena in order to measure temperature in different ways.
Very good. Well, I've really loved this book, and I love talking to you, and I hope we get to meet one day. And I just want to reiterate how enjoyable this book is for young and for old. The children of all ages, step right up, hear ye, hear ye. And we've been talking today with Nicole Yunger Halpern, who's a theoretical physicist, now at the University of Maryland. What is this Joint Quantum Institute? What is that? What was the raison d'etre for that?
The University of Maryland has a partnership with the National Institute of Standards and Technology, which is right nearby. Back a number of years ago, before every institution was trying to say, oh, we have a quantum institute and we're developing a quantum team, before quantum technologies and quantum information science were big deals that everyone's investing in as they are today, quantum information didn't exist as a field. It was very hard to get jobs, and no one would hire a quantum information scientist as a quantum information scientist. Just such positions didn't exist. But there were very few institutions that realized the promise of quantum information science and started investing in it early. The University of Maryland and the National Institute of Standards and Technology, NIST, formed a partnership to invest in quantum science, including quantum information science. So they created a joint institute called the Joint Quantum Institute, the JQI, and that was successful. Then another center was formed to be shared between NIST and the University of Maryland, and that's called QUICS, the Joint Center for Quantum Information and Computer Science. It's more mathematical and computer sciencey, whereas the JQI has more experimentalists. So that's actually partially what drew me to Maryland. It has this very rich, long history of investing in quantum science. So it has this massive quantum community with people from all different perspectives, from computer science and experiments and physics and engineering. It's been a lot of fun to participate in.
Well, that's wonderful. Well, Nicole, we've reached a time that is customary for my guests to go into the impossible. If you are willing, I would love to ask you my patented, thrilling 3 final questions. Are you willing to go into the impossible? Okay, we start the thrilling 3 with a question about your near-term future, and that has to do with something known as an ethical will. And that's a statement of wisdom or values that you most want to articulate to future generations when you leave this mortal coil at the age of 120 or beyond. And actually, you touch upon time reversal or time stabilization in the context of biological entities. I'll leave that lively description for those of the audience to read and devour. But I want to ask you, at 120, what ethical wisdom would you like to bequeath in your ethical will?
interpret that question as meaning, in my case, so what would you like to leave as your scientific ethical will? Because I feel like I can tackle that a little bit better than an ethical will that encompasses all of ethics, which I don't feel like enough of an expert on. So I've talked with a number of former students of Eddie Farhi, who is a professor of physics at MIT and now an employee at Google, because again, everyone's getting involved in quantum computing, including behemoths like Google. So according to one student, Eddie said once, when talking about writing science papers for the scientific literature, we make works of lasting value. And I think that that's a great motto to have. Nowadays, there is this atmosphere of publish or perish. So people sometimes crank out papers just as quickly as they can, even if the papers are not great advances. But I think that goal to shoot for is to create works of lasting value that we will be proud of for a long time and will have impact for a long time.
Lovely. The next question involves also the future, but maybe the future more of your field, and that involves this concept of Arthur C. Clarke evoked in 2001, A Space Odyssey, this concept of these monoliths, these giant, maybe quantum computers actually, but anyway, there are these giant monoliths, huge skull. We don't know what they are. They could be time capsules or whatever. I want to ask you, if you had to right now engrave a monolith or, encode within a monolith or put an SD card in a monolith with kind of a summary of what your field has accomplished and the thing that you collectively are most proud of your field, rather collectively, what have you noticed? What would you put on a monolith to brag and kind of beat your chest about and have a little swagger about in your field for some alien species to eventually find and be unable to, eject the USB drive in their spaceship?
I think it's remarkable that the laws of thermodynamics still stand. And again, they govern so very many other theories. Furthermore, we can write the laws of thermodynamics not only in the classical language in which they were first developed, but also in quantum language, so that it's clear how they govern classical and quantum systems, as well as information processing. So I think that the laws of thermodynamics as they apply to classical and quantum systems would be worth recording.
Good. Yeah, you mentioned the famous quote. I forget who said it, but if you violate some cosmological principle or even some conservation of momentum, as Pauli did at some point or tried to do, you can at least maybe not get too much trouble for that. But if you try to violate the laws of thermodynamics, there is no hope for you. So they're amazingly resilient, if nothing else. So that would be a great one. Okay, now we're going to go backwards in time, and now we're going to get personal. Although I know not everyone's comfortable with getting personal, but I do want to ask you a personal question, and it relates to the origin of this podcast. And it's related to Sir Arthur C. Clarke's third law, which states, the only way of discovering the limits of the possible is to venture a little way past them into the impossible. That's the origin of the name of the podcast. So I want to ask you, Nicole, what aspect of life or your work perplexed you, mystified you, 10, 15 years ago when you were younger, and but yet you overcame and had the courage to do as you've done and go into the impossible, including writing this magnificent book, which is a tremendous accomplishment.
Something that I didn't expect to be so possible was to have a liberal arts education so enrich my physics research. When I entered physics grad school, I was with students who had studied primarily physics and math for the past 4 years, whereas I had studied physics and math, but I had spent some of my time studying German literature and art history, and I felt different and behind. But I've found over the years that having a liberal arts education is so useful for my physics research. It helped teach me to bring together diverse ideas from very different disciplines and put them together. So to bridge fields and also gather information in ways that isn't always obvious if we have just a scientific training. So something that was surprisingly possible to me was to have a rich physics career that's been enhanced by a liberal arts education.
And that's wonderful. Well, Nicole, I want to thank you for coming on the Into the Impossible podcast for this book, which has received delightful praise from folks like Anna Weltman, author of Supermath, who called it Introducing Curious STEM-Inclined Novices to the Concept of Quantum Steampunk. Yunger Halpern fluidly weaves together a playful tone with a steampunk narrative and her own personal experiences. It's as much a memoir as it is an explication of some of the most fascinating, mystifying, and delightful concepts in all of science. And I want to thank you for coming on the show today, Nicole.
Thanks so much for having me here. It's been a pleasure.
Any sufficiently advanced technology is indistinguishable from magic.
Well, I hope you loved this fascinating journey into the impossible with Dr. Nicole Yunger Halpern as much as I did. We covered so much ground in quantum computing, thermodynamics, Maxwell's demon, and much more. I know if you love this interview, you'll definitely want to check out this special playlist that I created just for you. It contains my curated greatest hits on thermodynamics, the arrow of time, and even quantum computing with one of Nicole's advisors, John Preskill, the Feynman Professor of Physics at Caltech and a great friend. So, join me, click here for the special playlist, and don't forget to subscribe.